Okay, so yeah, any questions for last week? No? Sorry, not last week, last session, which is 2 weeks ago. No? Well, I'll assume that you haven't done the homework yet. Sorry, yeah. Basically, I just do some of the question and just keep push. Um, okay. Let me just explain the task again. So last week we have gone through chapter four. The homework was actually to implement parts in chapter four. Um, so, like, for example, finite groups, you can implement a finite group. You can make it simple, right? You can just implement finite groups for, let's say, prime, prime numbers, or you can just implement one of the finite groups. For example, the finite group for natural number order five, right? Finite group for five with with the addition operator. That's one thing, right? There's also like generators, exponential map, if you can. um, well, you can write a function that produces an exponential map, which works. Um, Factor groups, pairings. I think pairings is a little bit harder here, because I don't think they really go into like how it's done. I think this will be covered in chapter five. Hashing into groups. This is something that actually is a pretty straightforward because of all the code that's available. Rings, fields, implement fields, and make sure that you can do the addition and all that here. Um, Prime field extension, projective planes, and all. So that's essentially the homework itself. Yeah. So I'm gonna go through. Okay, so I'm gonna show you what I've done. And okay, so for me personally, what I find hardest to implement actually is the prime field extension, because you basically have to implement the concept of polynomials. This is one that I haven't written enough. I think my code is not currently working, so I'm experimenting with this still right now. But yeah, other than that, I've implemented mainly on the fields operation. So fields itself, projective planes, hashing into the field. So I've implemented that. I haven't tried implementing the try and increment yet here. This is interesting to implement itself, but this is not too hard because they do give you the code for it. Yeah, I do find the private extension itself being more tricky to do. Because you need to have the concept of so to say polynomials, right? Anyways, I'm gonna show you what I've done for prime field. So okay, so fields itself, actually it's not too difficult to implement. You are mainly you want to implement. So I'm using Python here. Tell me if you can't see. So I'm mainly using Python here. And as you can see, it's just a few elements, and the entire idea is essentially I'm implementing this to do general field operations. Yeah. Um, yeah. For those that do not know Python, all this double underscore just means it basically our implementation of actual operations in Python. I'll show you the code itself. But yeah, I've implemented field elements. So addition and multiplication is pretty easy. It's just doing addition and multiplication of two different field elements, and then doing a modulus of it, of the order. So here the order just refers to this, right? Like refers to this n itself, right? And yeah, subtraction, honestly also not that different. Um, this is power, so this we are basically just taking the power off the field. Also not that different. It's the same. Python doesn't really allow you to directly do like the exponential, so without having like overflow error. So yeah, you do have to know this. So you might overflow because you might overflow when you deal with exponential of very very high numbers, which is the case in hashing. But yeah, just this is just division. So division, remember we talked about Fermat's Slither theorem in chapter 3. where we basically um, it's basically a way of calculating in a multiplicative group, or so like how there's a way of calculating um the inverse of a field element, right? So in this case, yeah, division requires that. Basically, to divide A divide B, it's just A times the inverse of B, right? Math. So yeah, this equal is essentially just equivalence of two field elements, right? This you need it when you want to check that, hey, if a field element of field five is like, if three of field five is equal to, let's say, eight of field five, right? It should be the same. But yeah, that's the entire idea. So yeah, this is the field. There's also inverse. So this is just again Fermat's-Little theorem. I've also made a convenience function here, just to make sure that I can basically do what you see in the code base itself, where you can actually how do I put this? Where you can um basically it acts like what Sage does, right? Sage have this function of letting you define the field and then using the field to create. This is like a convenience function to do that. And I've written some tests for this. Um, yeah, I mean, you can just see how it's used, right? So test field creation. This is fields bigger than order. I'm just asserting some stuff. So this is just all tests. But yeah, this is how you use it essentially. You can just do like addition, subtraction, right? This doesn't work. You shouldn't be able to add fields of different, like elements from different fields, right? Yeah, so I mean, that's what I was expecting in the homework itself. Maybe I'll define it a little bit more clearer next time. But yeah, that's essentially it. So yeah, I've written some tests. You don't need to write tests for it. Just test it out at least. Here I'm writing tests for it because I just want to, might as well do it right properly. But yeah, I still recommend and highly recommend, once you go back home today, yeah, spend some time, do it. You don't need to show me. It's just a way of learning, right? Okay, anyways, hashing, I've only implemented the naive hash. So this is what's talked about in let's say hashing to groups. So here they are basically showing you, first of all, the truncate. Where is the truncate? K truncation hash. This one I didn't implement, but this one is pretty easy to implement. You just truncate your string, and then yeah, that's essentially it. But this is, first of all, it's very easy to do. You can try this, but this doesn't really have collision resistance. It's very simple to do it. So I've actually implemented this. So this actually has some code in it already, which is very convenient. And what I've done is essentially I'm just hashing to the cyclic group, and I'm just using SHA, right? This is also pretty easy to implement. You just have to understand what they are trying to do. I haven't done this yet, but yeah, it's quite easy to implement this sort of Peterson hashes. Of course, in this case, we are using SHA-256 with Peterson. Yeah, so it's not difficult to do that. But yeah, as you can see, a naive hash, this is the so to say the SHA-256 hash that has some problems because of I think they discussed about it over here. Yeah, there is a relation. You can very easily find a relation between two hashes. You can find a discrete log relation between HTS and HTT, which means that if you have HTS and HTT using this very naive hashing method of hashing over just a single generator in this case, you can just do some calculation and find out the relation between two hash values, which is not good. You don't want that because you can use that information to um, kind of easily help you break um, not break, but yeah, you can use it to do some stuff, do some shady stuff, and try to figure out what is actually being hashed. Not directly, you can't reverse the process, but yeah, you can find out the relation, and eventually, it helps you easier. It helps you to find out the underlying hash slightly easier. I mean, it's not very easy. I believe so, at least. It does help you. find out. From relation, you can eventually find out, I think. Yeah, the exact process, I'm not sure. But yeah, if you're interested, go look into it and maybe enlighten me on the next study group. So yeah, yeah, so I've implemented that here. Yeah, it's very simple. It's just generated to the power of this cipher's X value. I think it will be nicer if I just do this. Oh no, actually it won't be because this is actually a field, but this is a number. Yeah, yeah, it's fine. This might break if my actually it probably won't break. But yeah, this might break if this value is too big, I believe. But anyways, yeah, this is just a naive way of doing it. But the safer way of doing it is very similar to this. It's just that we have to implement this multiple group stuff. And actually, if we want to do more, so this is what I'll continue working on. I'll try to push this code either tomorrow or sometime later, but very likely just tomorrow. I have some stuff to work on there. But yeah, we can also look into this, which is hashing into modular arithmetic, where they try to. So the general problem we have here is that it's not too even. When you use just a simple hash. So they are just trying to distribute the hashed value a little bit wider. Um, that's the general idea for the methods here to reduce bias, I believe. Um, so yeah, anyways, that's what I've done. For the projective planes, so I have to test here. Projective planes essentially is just trying to find. I remember what projective planes is. So projective planes is essentially we add a new point of infinity and then we just make it like a sort of 3D coordinate style. It's not really 3D coordinate, I suppose, but yeah. And yeah, it's also very straightforward to implement. These are all convenience functions for me to create it. And you use it like this, right? Use it to so these are all tests. You use it to test if basically they are all correctly generated. So here I'm just basically trying to get all the points, the possible points here. Here I'm trying to see if it uh correctly works with the coordinates I provided it, and this is the order itself, and then so on, right? These are all just test cases. So I think the final lines one is just the question over here. So I just made this into a test case itself. But yeah, that's what I've done. Yeah, for this, you have to let your prime field have the ability to define polynomials. You can do that by just doing coefficients, right? You can use coefficients to represent polynomials, which is just a list of coefficients. That's good enough. But yeah, that's what I've done. I skipped group and rings because to be fair, or I mean to be honest, everything if you can implement the operations that I've mentioned, like hashing into fields, extension, projective planes. Essentially, there are similar things to what's in the groups and rings. Yeah, so I just only implemented the fields, all the operational fields and all that. Yeah. So far, any questions? The ones that have tried, do you have any problems implementing it? Okay. Hey, looking forward. So yeah, if you have any, if you have actually done this and you want to, I mean, or later on you have done this and you want to like just show your progress and whatnot, you can push your code to the fork repo and then just open a PR to the repo itself. And you can ask me questions there like, hey, can you take a look, see if this implementation makes sense? Yeah, I'm not limiting you to do it in any language. You can do it in any language to be honest. Yeah, but the entire idea is just to be so that we can discuss, we can talk about it, and you can kind of have like a kind of like a record of your um well, studies in your study group, right? Yeah. So yeah, I've put the instructions on the repo README. Essentially, yeah, just open a PR, open a branch, open a PR with that branch with your name on it. Write your name, put it in the folder with your name, and then um, submit it when you're done. I have a PR up. I think I just pushed it just now. You can take a look at it. I'll probably change the title to have my name on it later. But yeah, essentially, yeah, looking forward to it. Anyways, so now elliptic curves. I'm assuming some of you looked through this a little bit, so I'm gonna go section by section once again. And if you have any questions, stop me. If you don't have any questions, go for it. Um, so we'll only be covering the first three sections of chapter 5. We'll not be covering pairings today. So yeah, let's begin. Um, Stop me anytime, speak up, open your mic if you want to, or just type in the group. I'll be looking, right? Okay, so first, elliptic curves, short Weierstrass curves. Any questions here? A fine short Weierstrass form? Questions? Stop me. If I'm going too fast, stop me. It's good. Wait, let me just open this. Sorry. Yep. Oh, nice. Does it work for the online stage math? Okay. The plot. Let's see. Okay, so since you've mentioned it, let's I'll show it on my laptop, right? Might as well, right? Today we have less people. It's a good thing, in a way that now I can essentially give some special treatment. Um, Give me a moment. Let me just oop, put my okay. There we go. I hope you can see this. Let's do this. Okay, great. Yeah, if it's too small. Okay. So, um, I'll just do one plot to see that you see. So let's do Sage A equals F5. So this is in a field of 5. Oh, I have to define F5 equals the group first. So group 5. Sorry. Okay, A equals F5. B equals 5, 4. So F5, 6 times F5, 4 times A to the power of 3 plus. Oh, this is a polynomial essentially. Oh, no, actually, so this is essentially the form itself, the formula itself. So the affine short vector form is this. Where is it? Yeah, this. Right. That's why it's being written here. Okay, so I'm just going to continue this. Yep. 7 and speed of 2. I think I need to. There you go. Oh, it's fine. 2 not equals 5, 0. Is it this? Okay, true, which is correct. Now, let's do E equals elliptic curve. Oh, I spelled it wrong. And oh, sorry, this is not the form. I think this is just discriminant of it. Yeah, so this is the this is this. I'm very sorry. It's just checking this. Yeah. Anyways, okay. P equals E 02 A E dot XY 02. Infinity equals points on infinity, which is let's go to XY. Okay, sorry. Okay, X like X1. Yeah, zero division error. In this case, yeah, the infinity point and infinity does not really have a fine coordinate, which means that I mean it's used for calculation, but it's not really represented as a XY point in this case. So yeah, let's look at the plot, shall we? E dot plot. Ooh. Where is my plot? Where has my plot gone? That is a very interesting question. Where has my plot gone? It should pop up, but it's not popping up. I think I probably didn't set it up correctly. Unfortunate. Anyways, let me try to let me just do P. Oh yeah, I can. Yeah. There you go. Ta-da. Hmm. I have a feeling this is a bit. Oh yeah, it's F5. Yeah, it makes sense. Yeah, this is correct. Yes. Um, this image is like this because we are basically doing a field of order 5 over the elliptic curve, right? Over the so in this case is yeah, over this Weierstrass like Weierstrass form itself. So yeah, that's why. And this is a elliptic curve of yeah, so in this case, yeah. Yep, four orders. Yes, you're right. Absolutely correct. So yeah, it's correct. It's this. Yeah, anyways, yeah, this is confusing, but it should be just E dot plot, right? Yeah. If you do a little bit more, for example, tiny jab jab, it should show more. All right. If you have a bigger order, it should show more, by the way. Let's try you know what? Let's try this. Why not? We'll do the can I clear? Yeah. No, doesn't really clear correctly. Let me just clear here. Save yourself. So let's look at SECP 256 K1. So that's the curve that Ethereum and Bitcoin uses. Oh, this is bad. Oh, there you go. Yay. So let's see. P is prime because oh, it's not prime. I think I screwed up. Give me a moment. That's why. So this is the page number. There you go. Ah, P dot is prime. So I'm copying this straight uh from the book itself. That's why. So yeah, but he is prime. Let's do this should also be correct. And bits, yep. So let's create based on this and look at the generated graph. Yeah. Ta-da. How order? I mean, what's the order of this actually? I'm quite curious. Ooh, that's a huge order. Yeah, this is the basically just this number, right? The order of it is essentially the size of it, which is essentially yeah, the the number we're based on in the first place. So let's look at the plot. Oh, function has no plot. Ah, it didn't really. Oh, it's this, right? Plot. This should be a lot more. See if it pops up. Hmm, it's taking some time. Yeah, in the meantime. Okay. So anyways, yeah, that's that. I'll wait for it. As we wait for it, let's just go through the other sections. So okay, fine. Shopwise just form. Any questions here? Nope. Okay, let's go to isomorphic affine shopwise trust curve. Okay, why is this measure equation so special and what it tells us? Okay, so we are talking about this, right? So, so this essentially, this is special, or like what it tells us. Um, so this is actually in our beloved, um, well, quadratic equation, I believe, yeah. But anyways, yeah. So what this tells us is that, at least from my understanding of it, um, so so let A be equal to this minus not equal to zero. So this tells us that this cubic equation, um, well, let me collect my thoughts. I don't want to say it incorrectly. It's from my understanding. Um, so uh, hmm, well, so let me collect my thoughts for a little bit. Okay, so this I believe it comes from oh AB. Okay, so this cubic equation. Let's look at this cubic equation. If this, well, let's see what happens if this is equal to zero. Okay, so if this is equal to zero, um, essentially, uh, what happens is that if it's equal to zero, that means that they might, so that means that essentially the A and B value, right? This determines, or this shows, so to say, if the A and B value you selected, well, how do I put this? Results in a curve that have um, self-intersection. Self-intersection as in it intersects with itself. Like instead of first, so if you look at this graph that they provided, um, there's no intersection of the graph, um, right? And this itself, so without the intersection, so the intersection, what it will result in is it will create a very weird, not very weird, it will create behavior where we don't really want in a elliptic curve. At least once that, well, once that doesn't benefit us when we want to do, so later on we talk about this in our group law. So we want to do group law, and if it's not equals to zero, it means that there is some intersection of the graph to itself. And when we use the group law here, it will result in behavior that we do not want for a elliptical. So yeah, so when you choose your value for A and B in your construction of a curve using the Strauss form, um, you should use this to check essentially if the value you chose it's suitable to be used as an elliptic curve. Yeah, ZK, I believe you're right. So yeah, it's a method to select. Well, yeah, it has a method to select A and B. It's a method to check if A and B is suitable for your specific elliptic curve. Yes. Any more questions? Yeah, still plotting. I don't think my graph is coming up anytime soon. I'm just gonna stop it. I don't think I can stop it even. But anyways, yeah. Any more questions? Yeah, here it does explain it. There you go. Yeah, the equation ensures that curve is non-singular, which loosely means the curve has no cups or self-intersection in the geometric sense, even if seen as an actual curve. Yeah. So yes, let's continue. Yeah, stop me anytime if you have any questions, please. Yeah. So isomorphic affine short by short curve. Questions? Compressed representation. Affine group laws. Yeah, this is the what what curves can be described as an affine short wire Strauss. What special property they all share? Um, okay, let me just go here. So, well, I believe it's probably described here. So, to put it very generally, um, well, what curves can be described? Well, usually curves that you can so curves that is essentially described via this form, we call it the affine short Weierstrass form. So short Weierstrass curve itself, um, okay, how do I explain affine form? Yeah, yes, the equation itself, um, I mean the equation itself is one thing. So the affine form of short Weierstrass is this equation, and it does require you to define like a point of infinity. So this is used for um calculating the points you do not see. But yeah, so this okay. So let's read this through. Like so the short Weierstrass elliptic curve over F in its affine representation. So it's the set of all pairs that satisfy the short Weierstrass cubic equation together with distinguished symbol O, right? So from my understanding, this is the fine form. This is a fine representation. I believe there is another form for this. Yes, I believe so. I recall there was this yeah, I recall there's another way of like there's another representation of this. So a fine we like to use a fine representation here. I believe because it's pretty easy to understand on in the geometric sense. It's very easy to understand why like through this equation like or what it is. Um I believe that's why we use this form. Um, sorry, that's why we use this representation. There's another representation. I don't recall the name. I will need to go and look it up again. But yeah, so a fine representation is this. There's another representation. I don't recall the name. Um, yeah. What special property they all shared? So um, as for the special property, I think short-wise. Okay, so this book itself doesn't talk too much about its special property other than it is like this. It we can use the chord and tangent rule, which can be used for to represent uh phi means represent is it yeah I might have gotten things confused, but yeah that I believe we are using the affine form specifically. No, actually points are geometric. I'm pretty sure points are geometric. Yeah, but I forgot. I recall, right, I recall looking into this. I might be wrong. Yeah, yeah, but yeah, I'm not quite sure. But okay, I'll go back to the what statutory deviation. So one of the things that we want from Weierstrass curve, or actually from all the curves, in this case, um, is the ability to do the chord and tangent rule, right? We want this because we can use this, um, to represent our group operations. Um, so remember the addition and multiplication we have in our group. Um, so that essentially we can use the chord and tangent rule to actually represent in this or in the actually in the curves that we're going to discuss here. As for so the three curves that we are talking about here, right? It's very much very suitable, not very, I mean, it's very much more suitable for what we're gonna do in Snarks. I'm not very sure, but I'm pretty sure there are other elliptic curves that does not really fit into like in our use case of like cryptography or whatnot. But yeah, in cryptography, um, so what we are talking about, like what we are talking, like the curves that we are talking here about here, it's very much very suitable or like yeah, more suitable for cryptography when compared to all the possible curves out there. So yeah, probably also this possible to represent in two alternative called Montgomery and Twisted Edwards form. No, a fine representation is different from that. So a fine representation, there is a fine representation for all of this. Um, okay, I mean in Twisted Edwards case, we don't really talk about it like that. But yeah, there is a fine representation in all of them. There's another representation I really do not remember. But yeah, let's see. Yeah. There is yeah. Sorry. So the affine represent. Okay. Yeah, I remember now. So okay, so yeah, it actually gave me a pretty nice explanation here. Yeah. So oh no, it's not this. Yes, I think the another representation is called a projective representation, which is essentially this. Right? They represent it in this form with the point at infinity as well. I might be wrong, but yeah, I believe that I have some recollection of it. But yeah, I'm not still not too sure, but I'm pretty sure at the point. So yeah, a finite representation basically just do not concern itself with the points and infinity like the projective planes. Whereas if you use the projective representation, it will include that, I believe. I believe that's why we talk about a fine form, a fine representation because I mean, essentially, it's just saying, yeah, this specific um function with a point infinity that we can just use, right? Rather than we have us having this entire project planes. I believe that's why. I believe that's another representation that I was thinking about prior to this. But yeah, um, the twisted Edwards one and Montgomery is slightly different from this. So apparently here when we talk about a fine representation, it's just mainly about how we represent this in like how we actually describe this. It's yeah. Okay, I'm going to continue. So affine group law, scalar multiplication, logarithmic ordering, projective shock, Weierstrass form. Oh, here they talk about the projective form, projective representation, I believe. Is it? Yep. Projective group law. So this is talking about how the group law will look in the projective representation. So I mean, it's going to be fun if you try to implement this. Tell me if you did it. Yeah, this is probably a core group isomorphism. Yeah. So Montgomery curves. Any questions here? Fine coordinate transformation questions. Oh, okay. Yeah, good questions. Why do you want to use the Montgomery curves? Let me just click into that. Okay. So before well, why we want to use this is that it has additional properties, right? To put it very simply, it has additional properties. So one thing to note, later we're also going to talk about twisted Edwards curve. Um, Let me check if I remember incorrectly. Let me see, let me see, let me see, let me see, let me see. Okay. Yep, I'm pretty sure. Yeah, great. Okay, so um a Montgomery curve can be so okay, a Weierstrass curve might be a Montgomery curve. So they are a subset of Weierstrass curves, short Weierstrass curves that are Montgomery curves. So like more almost I think all Montgomery curves are Weierstrass, short Weierstrass curves. That they are valid short Weierstrass curves, but not all short Weierstrass curves are Montgomery curves. So in the case of why we want to use Montgomery curves, it's essentially that they have additional property that allows us to do computation slightly better, slightly easier, slightly more efficient. Um, they represent the same bunch of points. However, so they actually talk about it here. The curve looks different if you plot it out, right? I'm failing to plot it out. Sage is not responding. I think this is way too much point for it to compute. But anyways, um, Oh, my laptop is just hanging. Yeah, it's dying. Anyways, it's cancelled. Yeah, let's quit this. Um, Montgomery curves essentially is just so let's look at this. So those curves allow for constant time algorithm for scalar multiplication in this case, right? So um you can write some of the short Weierstrass curve in this form. And when you can write it in this form, it means that they are valid Montgomery curves. But yeah, not all of them. So that's the main reason why we want to use it. It's slightly more efficient in this case. And I'm just going to jump to twisted Edwards curve. So even in Montgomery curves, there is this problem of we still need to do group law, and group law there is some problems, not problems. I mean, there are branches, right? You have to define so look at this, right? So we have to handle the neutral element, the inverse element, the group laws of the group law. You need to handle it for each of these, right? They are all if statements essentially. Um, that's where twisted Edwards curves come in, right? So okay, so short Weierstrass curve. Here we talk about this. Essentially, um, actually we talk about all of this. Because they are pairing friendly, right? And so all of the curves we describe here are all pairing friendly, but um, short Weierstrass curve, which is pairing friendly, but perhaps but quite slow to compute. Mainly due to I think mainly due to the group law being hard to deal with because you actually need to define each of them. Like oh how do I do the chord rule and tangent rule? Whereas Montgomery curve, if you look at they have already defined it in um formulas that it's very easy to calculate as compared to the short Weierstrass curve where it's very much geometric. This is slightly easier to do calculation with because of its property. Um, and then we'll look into twisted Edwards curve, which is even easier to calculate because we can basically make it so there's only one operation. So this is actually related to the Montgomery curve as well. So um through one operation, it is very easy. I mean, twisted Edwards curves, I believe it's also like a subset of Montgomery curves, if I'm not wrong. Um, but essentially, this allows us to implement it in computer pretty easily. This is very friendly for a computer implementation, right? That's why we introduced to twisted Edwards curve. Um, of course, so a very interesting thing is a very interesting homework I would suppose is you try and implement all of this, because implementing I believe top two should be pretty hard. Yeah, do benchmark. So implementing these two should be pretty challenging. I'm not sure if I think it's possible to implement short Weierstrass form, like probably just difficult, but like twisted Edwards should be relatively easy to implement because of its property of being, um, I mean, this essentially is saying, yeah, I want to make it stuck friendly. We want to reduce as much branch as possible. Why is that the case? Well, we will actually talk about it later, but the branches are not friendly to snarks due to the fact that for each branch, so it reduce the determin like it reduce not reduce it makes it not deterministic, so to say. If you have branches, it makes it not deterministic. And in snarks, we want to deal with deterministic stuff. We want to represent um our program in polynomials which we can then operate on. And having a curve that has less branches, or like the operation like to do calculation curve that has no less branches, makes the implementation a lot friendlier to Snark. So yeah, and there's also the fact that it with less branches it uses, well, doesn't even use. I mean, I guess yeah, with less branches, it does make it so that you don't have to when you do calculation, you don't have to like well, you can share a lot more resources in a way, right? The field operation should be lesser in this case. Yeah. I will try to look into a little bit more into this so we can maybe talk about it next week. Yeah, but yeah, the best way to actually know about um okay, so I think probably the biggest comparison will be the Montgomery curves and the twisted outward curves because this essentially is a extension on the Montgomery curves itself. Like, but it's very friendly towards computer. Yeah, that's why we have this tree, right? We have all this because it's like that's the reason. So if you look at the twisted Edwards group law, it's just this compared to this. If you look at the group law here, click, it's this. So I mean, we basically have to deal with if it's the tangent rule, we need to calculate like this. If it's the chord rule, we need to do it like this. Whereas in twisted Edwards curve, we only do it like this. So this single thing allows us to so this equation, right? Allows us to essentially do this entire thing. So we don't have to deal with like if it's, this is the case we need to do this. If this is the case we need to do this. Um yeah, inverse as well. You don't need to say like if we have this, it's this, right? You can just do the calculation straightforward here. Yeah. So yeah, that's the three curves essentially. Short Weierstrass curve, which is a fine form, defined very simply. Have all the properties, you know, the projective form of it. We can look at the group law. So group law here, it's just as you can see, it's a little bit more abstract because it's just drawing a line and then determining that, right? But this is very easy to understand if you draw it on the paper because there's pictures for this. Simple and standard for all possible values, no special. Yeah, that's for the twisted Edwards curve, yes. So in this case, well, if you draw on if we draw on the graph, let me just find a picture, right? I think you'll probably see if you Google elliptic curve, you'll probably find this picture. Elliptic curve. Let me just search chord and tangent. Tangent. But actually this is essentially it, right? If you see this, yeah, this is chord and tangent rule. Um but yeah, chord and tangents. Yeah, there you go. Yeah, very easy to like to visualize this, right? You draw a line, it pass through this, and then we take the tangent of it. And then the other operation is just doing the same thing again and again and again and again, which results in the multi-points that you see, right? It will just continue, 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 continue. But this is very easy to explain in this short wire short course curves, right? When we talk about it. Um, However, when you want to do calculation, I mean in algebra or like x and y's, it's a lot easier to define like when you define it like so, right? Let me see where it is. Okay, I need to go down. Yeah, there you go. When you're defining like this, it's just a lot easier. Yeah, I need to close this, I think. Let me just close this. Yeah. Right. This is a lot easier to calculate now. We even without the points and all that, without the graph and all that, right? A lot easier to do. And then when we go to like computer implementation, be done in branch, just one thing, and then we can basically use this operation and just do all the calculations, right? And this will work. So yeah, that's the three curves. Any questions? I think if you are the type of person that really benefits from practical work and implementation, yeah, trying to implement this tree is going to help you a lot. Yeah. Any questions? If not, then I think we can probably call it a day today. Next week, um, so next week, we're going to be finally going to pairings and hashing in the curves. So actually the last three things, right? So these three, so 5.4 to 5.6, probably not into statements. We'll see how fast we go. But yeah, elliptic curves pairing is like one of the core ideas in Plonk in Graph 16, not in Fry, not in like the recent stuck based VMs, but they are core ideas. So yeah, it'll be quite exciting to do this. Yeah. Okay, we have one question. How to transform the two curves into twisted Edwards form? Um, I would say, well, transform into it. Hmm. It's very much dependent on the parameters you choose. So, in this case, it's A and D, right? In Weierstrass curves case, it's A and B. I think in Montgomery curves, it's also A and B. I believe there. I think I'm not sure if they actually talk about it here. No, I don't think they talk about it directly here. They do talk about Montgomery curves. How do you want to actually find it? Just yeah. So this is this is short wire straws. This is converting from Montgomery to short wire straws, I believe. Yeah. Um I wouldn't say transform it over. Okay, maybe you are right. It's okay. I'm not sure exactly how to do that, but um, you can't. You need to have a curve that is that can be a Montgomery curve, or like you need to have the curve to be, so to say. I don't think compatible is the right word. Yeah, but essentially you need to have, maybe compatible is right, but yeah, you have to have a curve that can also have the property of twisted Edwards curve. Um, if they are, then you can transform it over. How does one transform it over? Um, that is a very good question. Let me find out, and I'll come back to you on this actually, because they actually talk about like, hey, a twisted Edwards curve can go back to Montgomery, and a Montgomery curve can actually go back to short wire Strauss, like the form itself. They can go back because they are subsets of each other, from my understanding. Twisted Edwards is a little bit more. I'm pretty sure it's also a subset, but yeah. Anyways, they can go back. You can map it back. But they don't talk about how do they convert it over. But I believe it's possible. But you really need to know the parameters. Um, let me just record this. How to convert from. Okay, let me see. I asked if you're going to Alio, use BLS 12377 for pairings, but use the L form for hashes and commitments for efficiency purposes. Um, yes. Are you saying that they don't use the twisted Edwards form for other operations other than hashes and commitments? Of course, BLS itself might I mean they might just be using the twisted Edwards form for BLS curve, right? Um I'm not sure. This I'm not sure. But yeah, I mean to do share if I mean the code and whatnot, so we can all look into it. I think that's going to be interesting. Maybe next week we can look into it. Yeah. Um no, but like twisted Edwards, it's not a curve itself, it's a form to represent curves, right? Um because BRS 12377 is just a basically well, yeah, I'm not sure. Yeah, I'm not sure. Um pretty sure. I might be wrong. I might be wrong. Yeah. Because yes, twisted error form supposedly, yeah, it's going to be efficient for computation, right? So very likely they will just be using if they are going to use twisted error form for it anyways. Actually, I really have need to look into this. Because if they are going to do computation anyways, why not just use twisted error forms of the curve itself for everything, right? At least that's my understanding of it. Since it's um more efficient in this case. But who knows? They might want to use some other form for specific computational purpose as well. Yeah, I'm not 100% sure on this. I'll actually need to look into it. But that's a very interesting thing to look into actually. Yeah. Do they use other forms and then change? We can look into this. Yeah. Yep. So next week we're going to cover elliptical pairings, hashing, and constructing ellipticals. Um, Homework is to try implementing these three. It's gonna make you learn a lot more through hands-on experience. So yeah, do that. Last week's homework on the algebra on chapter 4, I'll push it tomorrow night probably. Um, so for those that want to look at how the code might look like and play with it, we can look at the repo. Um, or you can just do it yourself first, submit the PR, and then look at what I've written, right? That'll be great. Yeah. So I think that is all for today. We'll do pairings next week. So this is our fourth session, fifth session, fourth or fifth session. We have like 4 or 5 more to go. We're going to go through statements, circuit compilers, and finally this. So we are actually going into very exciting parts of CK proofs. So if the curves is actually very interesting, the pairings is very interesting in my opinion, because um this is what well, a lot of, I mean, leave the curve itself is very interesting because it's what modern cryptography rely on quite a lot, right? Yeah. So, anyways, thank you very much for coming once again. I look forward to seeing each and every one of you next week. And if you have any questions, please tell me. Please send it to the group. If you're not in the Telegram group already, you should tell me now so I can send you the link. But if you're already in, ask questions in there, and everything. Thank you very much for your attention. I hope you enjoyed it. And yeah, that's it for today. Have a great night. Bye bye.